Okay, well, for people who are joining this live stream, we are exploring some creatures in the wilds of the computational universe related to combinators. These kind of show us analogies to various features of physics, but also there's a 100th anniversary of combinators coming up, and so I've been exploring them for that reason. And actually, hold on 1 second while I restart something here. Otherwise, I will not be able to get any interesting messages people send. Okay. Right. So, okay. So let's just recall. So one thing we're trying to do is we're trying to understand when we have a combinator expression, there is a whole issue of its evaluation front, which I want to talk about, and I want to talk about the ways to parameterize the evaluation front, and then I want to talk about what you can evaluate. In other words, normally when people talk about combinators, they talk about compiling lambda expressions into combinators, but I want to talk about if you just enumerate possible combinator expressions, what lambda expressions do you get out, if that makes sense. Roman, are you with me?
Yes, I'm listening.
Well, right. Okay. So what I tried to do here, so let's see if I can do this a little bit more cleanly. So I'm going to do this with SK, with the standard combinators. So this is now, okay, so this is the SK rules. So those are the standard combinator rules from nearly 100 years ago now. Okay, so now what I'm trying to do here is what I think I'm doing. Let me see if I've got it down here. Is that I'm saying which combinators, so okay, so what's this? Enumerate combinators. So this is an attempt, and I'm not sure this is the right way to do it. Hold on, let me try and get enumerate combinators, locate expressions. Okay, locate expressions up to, all right, so what I'm trying to do is, given a combinator expression, okay, so let me write down a random combinator expression. I want to find out all right, the idea of this is given a particular, okay, let's take a look at how this works. So let's say S of K of, I don't know what I have, of S of K of whatever, I don't know, some random expression there. So now I can, if I give that two variables, okay, so let's say I say of A of B, and then I say / dot SK rules. What? Oh, I didn't evaluate that. Okay, that whole thing turns into A of B, right? So my question is, as I enumerate different combinator expressions, what essentially lambda expressions do they turn into? Does that make sense?
Mm-hmm. Yes, I mean, obviously, given enough of these, I mean, any expression is ultimately expressible in terms of S and K.
Well, I know that, but we're looking at that explicitly so that we can look at it for other things than S and K and see how that works. See what I'm saying?
So you're starting with simple
No,
simple
look,
expressions building up? Or?
look. Yeah, here's what I'm doing. Here's an example of what I'm doing. So what I'm saying is, given, I'm saying, okay, so here, what I've got is for a given, let's say 4 here, that's all the SK expressions with 4 things in them. Okay? So for each of these, I can now ask, what are they really? Do you see what I'm saying?
Yes, so you
If I
apply them
say,
to A and B and reduce them, yes.
right, so if I do this now, if I apply this AB thing here, / dot / at this, right, I get this. Now, some of these still have S's and K's in them.
Yes.
Right? So those I'm treating as not, as sort of syntax errors. Is that a reasonable thing to do?
Yeah, I mean, if you're looking for functions of 2 variables, yes, then obviously if
Right.
it's well
If the S's
defined,
and K's are,
yes.
are left in there, that doesn't work. Right. So to get valid lambda, because those aren't lambda, to get valid lambda expressions, we need cases where all S's and K's reduce out. Do you agree?
Yes.
So then what I'm asking is, okay, so question, for a given lambda term, what is the simplest SK expression equivalent to it? And then sub-question, what is an example of is there an example of a lambda I term that cannot be reproduced with S alone? There better be, otherwise S would be universal.
Yeah, which it isn't. I mean, if you don't have K, then you need the other 2 composition operators, right? B and C. Because what S does, S sticks its third argument into each of the first 2 arguments.
Right.
So if one of these doesn't need it, you either need K to eat it alive, or then you need a separate, simpler composition operator.
Well, so you claim, but I'd like to know what's the first lambda I term that cannot be reproduced with S alone? You see what I'm saying? So we should be able to work that out. Let's try and do that. Let's try and figure that out, right? So the issue is there will be some things where the S expressions don't terminate, right? And do you think it's important? Is / dot enough to use here, or should we use leftmost outermost to get the highest probability of termination?
Well, for these small terms, I mean, well, obviously, I mean, there's at some point you will have a sub-expression of the form SII in there, and then you will get non-termination. But before that, I mean, you can start with simple / dot and see if there are cases that don't terminate, and we can always look at them in detail.
Right, but I mean, I could equally well just use leftmost outermost, but it's somewhat slower. So let's use / dot. But again, I would really like to parameterize. I mean, a sub-objective here is to parameterize, / dot versus leftmost outermost. In fact, let's start writing out that issue. Okay, so let me just save this here.
So we want a form of replacement where you can specify the strategy, right? And probably also
that's correct.
Some maximum number of applications before it gives up and so on.
Right. Version replacement, specifying strategy. Okay, so now I could go back to SMP because I had a version of this in SMP.
Yeah, we looked at this once.
Right. Yeah. And what it did, so, okay, but maybe we should look at it here. And I mean, clearly what's going to happen here in terms of multi-way systems is we're asking, what, I mean, maybe we should take an example of one of the non-terminating combinator cases. Where is that one? There's an SK one, there's an pure S one. Let's see, I'm sure I've got that someplace here. I also want to actually show the confluence property of combinators in a nice way. Where is the S one? Oh gosh. There's S. Okay, and this is the leftmost outermost evaluation. Oh, S outer evolve list. Okay, so that's the one which does an outermost evolution. Right, so what that's doing is it's saying for each of these, only allow, oh boy, this is almost exactly the simp parameter of SMP, is how many to allow, right? How many updates to allow.
How does it specify that it goes from the outside to the inside?
Because that's what /dot does.
Okay.
But we can certainly have a strategy here where we have a different number that are allowed, right? We can say just less than max here. See what I'm saying?
Mm-hmm.
I mean, in general, then this becomes okay, but now here, what the heck is this? Is this the first one that is? Okay, so this is the first one that blows up. That's the case. So that's asking it. In this particular case, it's sorting by. So this is another way of doing the strategy. Mm-hmm. It's got it's got those positions. It's saying, where does the match occur? Okay, so where am I going to do
the short positions first, the outermost ones? Yes.
Right. Right. But I mean, in general, we want a strategy. In general, this is a story of kind of foliating the multi-way graph, because if we look at this thing, I'm sure I have a picture of it here. Let me just evaluate this and see what it does. I have a handy function that makes should make combinator evolution graph. Oh, it's a nest graph of that. Okay. Oh. Okay, fine. So this is, okay, so combinator evolution graph of the rules, which is in this case just this thing. And the initial condition, which is in this case just this. Oh, come on, what's
Probably
happened here?
need a list around the first argument.
Okay, 5 steps, we just get that. What's going on here? Oh my gosh. That is so freaking crazy. Let's look at the vertex labels. That was uninspiring. Oh no, look at the crazy things.
Oh, okay. It's got rather big.
Well, so the question is, where is the branch point? So in other words, here, right?
Mm-hmm.
Right. So what we want to do with this thing is we want to say, okay, with G equals this, then we want to say, in the vertex list of G, we want to say, select first of vertex out degree of G, comma hash is greater than 1, if I'm correct. Look at that crazy thing. Look at that crazy thing. So that's the first combinator that in this evaluation scheme has 2 successors, right?
Yes. Now, did we lose anything by ignoring the inner evaluations or not? Probably not, because I mean the S terms don't destroy anything, so you're not actually losing anything by.
Well, let's find out where the evaluations actually were. I mean, so this is, my gosh, look at this creature. Look at this creature. That's the first one that has an ambiguous. So actually, another interesting question is, who has an ambiguous successor? Right? In other words, if we simply enumerate let's see, combinator step. Yes, I think we can do this. Let's do this. We say combinator step of, and let's do the S term only. And then let's say of that on this. And then we want to do that against groupings of table, let's say S, comma 3, comma construct arrow 2. That will give us the all possible S terms. Oh, that didn't, yeah, right. So that has no success, right? Nothing. So that this is like, okay, so here, most of these have just one successor, right? Some have, some don't evolve at all. Some are fixed points, but most have just one successor, right? So now if we say select, let's say select in groupings of this, and now I say length of combinator step blah is greater than 1. Okay, nobody there. Okay, so let's go to 7. Oh, exciting, exciting. Okay, so those combinators have multiple successors. So let's find out what their evolution tree is and whether they have big branching or whether they actually just terminate. Well, there they are. They have branching, but they terminate anyway. Somebody's asking up here what the different shades of these nodes mean. I think those nodes try to label. They have, I think, S's in them. So some of them are leaf nodes. The leaf nodes have little tiny S's written in them, but hard to see. Okay, but so these are cases where there is actually. Let me just, to be complete, let me just run this against all of the up to size 7. Let me just run this n up to size 7, just to make sure that we got this right, that there were no earlier branches. No, those are the earliest branching ones. Okay, so let's try size 8, and let's see whether any of the size 8 ones have a... okay, so at size 8 we have that.
Now, is the 10 in there actually suppressing some of those that might actually branch again?
Probably, yeah, but the ones which have now sort of pooped out and gone to a single one, those are done. But there are a few here that branch again.
But what happens if you reach that 10? Do you see whether they die or whether they just stop after 10?
Honestly, you don't see if they die out. I mean, we're not correctly doing that. Okay, although I mean, if we just count here, we can plainly see these are gone by before 10. Right, so here we've got basically 2 that puff out, right? And don't terminate. Now,
is that striking difference due to the graph embedding, or is there more to it?
It's just graph embedding. It just has a complicated tree structure, and this thing is going to multiply up. This thing's going to get very big very quickly.
Yes.
So that's the halting problem basically for S combinators. And this is showing that there's a non-trivial halting problem. And we can compute the halting probability for S combinators from this. Right? I mean, the halting probability is basically, there's just 2 of these things out of the S8s. Out of the case of 8, this is basically telling us that the halting probability, non-halting probability, is 2 over 429. So what this is telling us, okay, so what we should be thinking about here, well, let's look at the case of 9, just for the hell of it, just to get a bit more intuition. But I think it's going to look very much the same. At least that's my theory. Okay. Okay, so these are the 9 branches. 180 of them. Okay. I wonder whether I can say tiny there. Let's see. Let me just put this. Oh, this is some stupid bug. I really need to fix this bug. This is a, okay, what is wrong with this? This is nest graph. Oh, I didn't pass the options to nest graph. Okay, let me just fix that. Let's try this again. I should maybe not have used 13 there, or I should have used my parallel machines. Let's not use 13. Let's use 10. And I'm just going to do this one. If this doesn't work this time, I'll use the parallel machines. I think it's time to use parallel machines. Oh no, there we go. Okay. So we have quite a few that branch here. Some that terminate. That's a jolly one. That's kind of fun. It's knitting that looks like it's knitting an actual manifold. Wow, I had no idea that combinators could knit manifolds. I want to see that one do its thing. I mean, because mostly
that's an interesting universe, maybe.
Yeah, well, quite. It's
there's one, a wild one.
This one here
on the right. Yeah, there's even 2 lines further down.
Oh, I see it. What's interesting about these is they're not growing that rapidly. Some of them are just exponentially growing, and they're just going to puff out. Yeah, this one here, I suspect, is just exponentially growing. Let's take a look. Actually, it's not so clear. Well, let's find out what the dimension of these structures is, because that isn't obvious. Oh, look, that's an interesting one again. That's that same deal that we had before of okay, I agree that these are interesting because they're not growing that rapidly on the edges. Let's look at this guy. Boy, it is the story of my life. I look at pictures, I generate collections of interesting potential creatures, and then I study them. This is what I always do. It's like it always ends up being the same thing. Okay, let's take a look at this. Okay, so this is the 10 case. So let's look at this let's look at the 8 case for that. Boy, this is weird. Oh, this bug is still not fixed. Could somebody report that, please? The double border bug in 12.2.
Yep. Okay. Got that down.
Let's do this. Let's make a graph 3D out of this guy. It's definitely making a kind of grid-like structure. Let's see if that survives further investigation. Interesting. Okay, let's keep going a bit. I did 10. Let's go to 11. Is that terminated? Has that terminated? The question is, what's the busy beaver S combinator that takes the longest possible time to terminate? It's terminated. It terminated. I'm telling you, there's always any time you think you figured out how these creatures behave, they will always do something you don't expect. All right, let's try this one here. All right, what's going on in this creature? Well, what's interesting about that creature is it's not like it's getting a lot bigger quickly. So let's just try doing this. Well, who knows? Let's see, if we look at this graph and we look at the neighborhoods in this graph, What can we see here? We should be able to see what the growth rate of these neighborhoods is. I think if we start with, so this is that, starting with this initial state. Did I get this wrong? Graph neighborhood volumes. Of a graph. Maybe I have to put that in a list. Oh my, okay. It's starting parallel kernels anyway. You know, this was supposed to be fixed. This launch dialog was supposed to look different.
I have a screenshot for it.
Could you send that in, please?
Yep.
So,
Who would? That's John, right?
well, actually, Roman, you'd be the one who'd be involved in this.
Well, as soon as I have the specification of that presumed new function for progress dialog, then I can hook it up.
Well, there is that exists. So that's a project management thing. I'm not sure. Ask Sushma.
Will do. Thank you.
Okay, let's look at that sequence for a second. What is that? Look at that puppy. It's not uniform. I'm telling you, these creatures are, they just, every time you think you know what's going on, they show you that you don't. So this is the graph neighborhood. So this is the number of things you can get to. Now each combinator step here is, I think, a single update. I think that's right. Let me just check this here. Yes, it is. It maps over all positions at which the combinator applies. So this is asking, okay, boy, our friend Mr. Schoenfinkel really did figure out something quite interesting back in 1920. I mean, it's like, how could he have figured out what this thing would possibly do? Absent, 100 parallel cores. I did find, I was looking at the works of Felix Klein, and I find this book about arithmetic and algebra. I don't know exactly from when, around 1900, I think, 1910 maybe. And he's talking about arithmetic. And there, to illustrate arithmetic concretely, he goes computational, which means he has a picture of a Brunswicker mechanical calculator. And he explains how the gearing works on the cogs to do certain kinds of computations. So even though Klein was a fancy pure mathematician, at least in those days, there was no snobbery about the computational world. All right, let's try and get two more terms here.
Were these questions of growth or non-termination even considered at that time? I mean,
I'm not sure.
Right?
Well, the Einstein's problem, the guy who finished Schoenfinkel's paper, Bayman,
yes,
he claimed that he had come up with the, and how do you say that?
Entscheidungsproblem. Yeah, that was the 1929 paper with Bernays, right? That's the other one.
Well, no, that's the other Schoenfinkel one, but that is about a different decision problem.
Yes.
For monadic predicate calculus, I think. This one is a 1927 paper. No. The main Schoenfinkel paper is 1924, but this paper by Bayman is 1927, in which he introduces this idea of an Entscheidens problem, and I think which he does because he's obsessed with Whitehead-Russell Principia Mathematica, and he is absolutely thrilled with the idea of types as a way to avoid, paradox, inconsistencies. Antimonies, I guess he calls them, particularly associated with transfinite numbers. Let me just get this out. Hold on a second. That is really weird. That's really weird. All right, let's see if we can get this to go further. Do we have the nerve to try 20? Let's try 20, see what happens. We have no idea what this is going to do, so whether this is going to terminate or, it's obviously not, it's not going to, I don't think it's going to terminate. But who knows? Maybe this thing will get to, some tetration-sized number and then terminate. Now, if we were used a theorem prover, could we tell anything about this?
But it's known, well, it's decidable whether it terminates or not, right? So
I'm not sure it is. I think people have claimed that, but the paper that claimed that.
Yeah, I need to find. I know the guy who started this whole question of S alone combinators, and at that time, he didn't know. But then apparently the question was decided, but I don't know which way. So I can ask him.
Well, I think that would these people like Berendrecht and Klopp, who we're meeting next week, they would know this presumably, but I don't even necessarily believe that paper because it was rather complicated and didn't have any computations in it.
No, I can ask the expert on S combinators.
There has to be one of those in the world. Okay, this isn't even. Oh, there it did abort. Okay, let's go to 17 or something. Let's see if what did I go to before? Did I go to 15 before?
15 was before, yes.
Okay. So let's see if we can make it to 17 and see whether it wiggles down again. Or whether it just keeps going up. If it keeps going up, it's going to be more and more difficult to compute. Although actually, I suspect that this computation could be done more efficiently because I don't actually need to keep all the stuff for this evolution graph. I just need to keep each successive step. I just need to map over each successive step, although I don't think the graph overhead is going to be very high.
Yeah, but we clearly need at some point, we need a built-in version of this parallel outermost or parallel innermost evolution strategies, right?
Right. Well, so let's look at, that was what we were originally talking about here, was strategies for evaluation strategies. This is crazy. How could it be? It's only 2 more. Even if it was 3, that's 10 times. It's not too bad. Well, let's let it compute for a second while we make a strategy for what we're trying to do. So we've got 2 different things. We've got the understanding of the, I want to go back and try and figure out the sort of compiled, what can S combinators compute? You see what I'm saying? In other words,
but that's a slightly different problem, right? You take an S term and apply it to some arguments and see what happens.
Exactly.
So and here you're kind of having S terms alone and are interested in those that do not terminate.
Well, I'm also interested in, oh, there we go, we got it.
Oh. Wow, that rises steeply.
Well, let's see what it's doing. Oh, this is crazy. This is crazy. How could it do that? After running for this number of steps, then it suddenly starts taking off. So another question is how big the trees get by this size. They may be completely huge.
So that those numbers that we see, those are the.
That's the number of, given that we start with a single term here, that's the, and given that we do n updates, that's the number of distinct objects that we reach after n updates that we have not reached before. Okay. So each one of those is a different combinator tree, 354,000 combinator trees at the end there. And any tree that we would have reached before, we do not count in that. This is the graph. This is, if you look at layers in the graph, this is going successive layers in the graph. Okay, so the graph in question is this elegant puppy here. So if we look at that graph, let's look at a slightly smaller version of that graph. Oh gosh, it's already a total mess. Well, who knows? Let's look at the 10 version and let's say graph layout goes to layer digraph embedding, aspect ratio 1/2. Okay, so that's what this looks like. So what's happening is, this is really weird. So what happens is, I think I know what's happening here. Okay, I think I know what's happening. As the terms get big, that's essentially an extension of the combinator in space, in some sense. And what's happening here is that there are multiple events that can happen at different places in space. See here, there's only one place in the combinator that the expressions can that the updates can happen. So I reckon if I go to, let's look at 9 here. That's not what I wanted to do. Stop. Okay, if we look at 9, it's going to look like that. Okay, so then we have a little growth there. So let's look at 11. And now one thing we could do is to say how big is the, you see here.
Okay, but there are still nodes that only terminate because you have run out of steps, right?
Exactly.
Okay, so this is not the true picture of how it would evolve further.
Well, right, and so maybe what
looking at the bottom, yes, where I mean it doesn't really converge, but the other ones just have reached their 11 steps, right?
Right. Well, let's indicate. Which nodes here are terminal nodes? And we can do that by simply asking, we can say, if we call this G for graph, or CG for combinator graph. Okay, now we want to indicate which are the terminal nodes. And to do that, we just simply have to say which ones are not going to evolve anymore. Okay, so what we can do there is we can just say, if we just say combinator step, so let me just check this works. So combinator step of that, okay, that gives rise to 2 nodes. That's right. Okay, so then say length of combinator step of this comma hash. That's going to tell us whether it evolves equals 0. So let's say highlight graph of CG, and then let's say this thing, and then let's say hash goes to, no, we just need to map this over the vertex list of CG. And that's going to show us which ones. Okay, great. Oh, let's see, how do I do this with a style that is, I think if I say style red, point size, is that going to work for a style? Well, let's try it, 0.1, for example. Or maybe none of them have terminated. It's perfectly possible that none of them have terminated. Let's just check that this code is right on something which does terminate, like this guy. I think that terminates there, so why isn't this showing that? All right, let's do this. Oh, I'm being completely stupid here. Sorry, this is completely stupid. This should be select in vertex list of CG, length of the combinator equals 0. Well, we're still not seeing anything, but I'm not sure that we should. So let's just try this. Yeah, okay, so there's,
Okay. Oh, there it is.
yeah, there's one terminated thing. So that is, because there's confluence in combinators, there is a single unique terminating state, which is kind of cool in this picture, to be honest. It's kind of cool that you can see that. So if we take this thing here and we do, okay.
Oh, there it is.
Wow. How could Schoenfinkel have known? That's pretty nice that that thing is confluent. Look, I mean, it's confluent and it terminates. It's like it's a black hole type thing. Okay. All right. So let's go back. And okay, so I want to answer the question: what can you make out of S's? Okay. How was I doing this? I think it was 12. Okay. Okay, so let's do this purely for S terms. Okay. What can you make? What functions can you make with S combinators alone? By the way, I'm still obsessing slightly about this, about what happens over here. Because did you understand my comment about space? The point is that you can think about a combinator expression as having, if it was as having a certain extent in space, in the sense that although it is not a linear, although it's a tree, you're saying it has many sort of pieces of that tree. And so what's happening when this thing goes crazy and starts generating many different cases, what's happening there, it's like physical space in the universe, where basically there are updates that can happen in many different places in space. If space is tiny, if there are very few points of space, there are a limited set of updates that can happen. But as soon as you can have many updates that could possibly be in parallel, you can have a situation like this. And what's kind of interesting about this is that then to define what it means to have a state of space, you're essentially foliating this graph by saying, because this graph defines a partially ordered set. And you're saying each one of these nodes is an event in this graph. And no, I'm sorry, each one is a state. And so each one is go ahead.
I mean, what's also about these S terms, I mean, there's lots of smaller copies of itself, right? I mean, they have a certain fractal nature because the S term duplicates arguments, and so you have smaller pieces of itself inside. I mean, you can.
How would we see that?
Well, I mean, you have all these nodes which, if you follow each of them, they kind of look the same, right? I mean, this doesn't happen here because here it dies out. But if it doesn't die, if it grows, then it has these smaller copies.
Let's try and visualize for a second. Okay, so we've got like the minimal one that blows up. Where is the minimal one that blows up? Minimal one that blows up is thing number 5 here. 1, 2, 3, 4, 5. That's really low tech. Actually, I don't even need to use that low tech method. I can just use this thing up here. That's the first one that blows up, right? And so here, and like this thing here, right? So let's take this here. This is actually, which step is that? 1, 2, 3, 4. That's the 11th step, I believe. But anyway, let's take that as an example. Oh, that's what we tried to visualize here. That's what that is. So if we say combinator tree of %21, graph layout, okay, there it is. So that's that term and all the things. So,
and I mean, you can see all the copies are essentially the same, right?
Well, okay. So if we wanted to visualize this nicely, we could do sort of a common subexpression play on this. So we could write this in terms of its common subexpressions, although obviously there's a triviality to that in the end, because in the end, when we sort of common subexpression the thing all the way back to the beginning, we'll just get the evolution of the combinator. But my question is, how can we draw this? What is a way to visualize this tree that's useful? Let me see this decidability result, because I'm really not convinced. I have a bad feeling that what they've proved is decidability of some property that isn't that's not the whole story, so to speak. If that makes sense. I think this is different. Yeah, I think that's a different thing. Okay, let's go back to this. All right, so we're going to go back to the question of what can we get from S's? Okay, so that's asking given an S combinator expression. So let's look at S's alone. So this is groupings of table of S, comma, let's say 5, construct arrow 2. Okay, so those are all the S terms, right?
Mm-hmm.
So now what we want to say is, for example, and now we're just going to do / dot this thing. Okay, hold on.
I mean, you could just start adding a single argument and see what happens.
I know. That's what I'm going to do.
And
yeah.
then to those that survive, you add a second argument and see what happens. And so on.
Oh, that's a good idea. Okay, let's try this then. Okay, so this is now, whoops, / dot that thing. Okay, so many of these, they get left with S's, right?
Yes.
Okay, so let's look at what happens if I do 2 arguments here. Okay, so do any of them not get left with S's? Okay, so what we have to do now is a select free q hash comma s, right?
Mm-hmm.
Okay. So now let's try the 1 argument case, and let's try 6, for example. Is it obvious that this can never work?
Well, I mean, even if you have a single, if the single table S, 1, you have S alone, right? And if you supply 3 arguments, then S goes away.
Okay, but that's 3 arguments. So let's try. Okay, but let's see whether we can get with 1 argument. Let's see whether anything. Oh, for goodness sake, what's happening
here? No, it could. I mean, there are those that explode, right?
Right. So let's do a time constraint of that. I'm going to assume that the time constraint, I mean, this is a hack because the time constraint could lead to one that has a particular property, but is, okay, so this time constraint is a hack. Oh, I could use the new confirm and close framework. Think. Why does it say aborted? Oh, because they're not, wait a minute, because there is aborted free Q of S? Wow, that's convenient. I would like to use confirm and close. Let me see how I would do that. I'm not sure, but anyway, this is okay. So we're okay here. Okay, let's just try. All right, so let's try the BAB case here. Okay, same 2 guys failing. Okay. That is definitely not a simple puppy. Look at that thing. Wow, that's so freaking weird. Okay, well, let's try the 3 argument case for smaller versions, for smaller cases here. Oh, okay, so let's look at this. Let's go N there, and let's make a table of those. So I think this is saying that the S, I mean, what you already observed, that the S combinator, if it has 3 things in it, can have non-trivial.
I mean, you could still have a term like SSS that just requires no, that requires a single argument, but then there are s's left. Yes, so eventually you need 3 arguments for every s that is left in there.
Right, but the fact that there's s's left doesn't necessarily kill computation universality. Okay, so let's look at this. So let's say length / at this. I see. All right, let's just try and do the 8 and 9 cases. Just see how many expressions we get. Oh, it's crazy. You know, non-halting or undecidability is such a pain.
Yes.
Still, it's what keeps life interesting. If everything always halted, if everything was always decidable, we wouldn't have to do this experiment because we'd already.
I'm wondering whether there's a better way to control the non-termination, because you no longer have only s's in there, but you still have these ABCs in there. So as soon as all the s's are gone, then it terminates, right? So as long as it doesn't terminate, you still have s's in there, and you need to continue to see what happens. So probably.
What's your point?
Well, I'm trying to get a better handle of when to stop searching rather than this time constraint. I mean, the other thing is that, are you still using outermost now? Or?
No, I'm not. I'm not using outermost.
But it doesn't really matter because it doesn't destroy anything. So I think it doesn't matter.
Right. I mean, well, we should be running this on more machines, but
then you cannot use time constraint. But
yes, I can on an individual one.
Yes. Okay, that's right. Yes.
Let's just do that. Hold on 1 second here. So this thing here should be a parallel map monitored. All right, let's use your beautiful parallel computation stuff. He says, it's a bad sign that it's not giving me the monitoring. God, this is pretty painful.
So this is now for n equals 8, right? That's the first case.
Right.
And this is the second one.
Right, and it'll be 100 times faster than what we did before. So ETA is 2 minutes. Assuming it's roughly uniform, which probably is.
Now, if we want to search for interesting functions that you can express with S alone, then we would really hope to see some simple A and B, ABC terms, right? Otherwise,
yes, I suppose.
Otherwise, there isn't really anything useful so far.
Well, but I mean, the fact is, if you're trying to do universal computation, there's nothing that says you can't strip S's out of your results.
Mm-hmm.
I really think we need to see this paper that claims that S's are decidable, because I don't believe it.
No, I can ask about it.
Yeah. I think what's decidable is something like the halting problem, perhaps. In other words, for what S is, do you get non-termination?
Mm-hmm.
Even that, I'm not sure. But like, Now, I mean, K, what does K do here? K really helps prune things down for the lambda terms.
Yes, I mean, the problem with S is that it always puts its third arguments into both subtrees, and so it goes and goes and goes.
Right. Hold on.
Because, for example, a simple function.
Just a minute. Flatten. Okay, so these are the expressions. These are the expressions that can be obtained using S's alone with three arguments.
Also seem to have some nesting structure.
Yeah, but they're trees, so why wouldn't they? I mean.
No, but I mean some self-similarity also. I mean, this is just a larger version of this one.
I'm not convinced. Look at it more carefully. I'm not convinced. This is I mean, you're claiming that they successively refine, and that they're the same object but successively refined.
I mean, I'm just thinking of the S terms we looked at before, which have this kind of structure. And if you then put in A's and B's and C's in these places, then, but of course, I mean, it could be very subtle. So it's difficult to see by eye whether subtree is identical to another one or not. But,
right. But so the question is, let's see. Let's see. Oh, this is the guy. This is the guy. This is the S combinator guy. This is the paper.
I mean, it's interesting in the abstract. It says something about the surprisingly rich structures, but if you look
the first
in the
part
paper,
shows
you don't
that
see
the term rewriting admits no ground loops. What the heck is a ground loop? Is that what makes my headset buzz? No. Procedure that decides whether an S term has a normal form. Right, but that whether an S term has a normal form, in other words, whether it terminates.
Yes.
Okay. And the fact that it is known whether it terminates is taken to imply that it is decidable.
Yes, and the way he does it apparently is by identifying building laws for those that go forever. So they have these structures. So there is
Theorem 55, there is a procedure. You know, I do not trust these things. I don't trust it. That it says, show me an algorithm. Existence is not enough. I'm not. Classify the set N of normal forms according to the existence of certain subterms. This is exactly the case where you need an automated proof, because it's just hopeless to do this. You know, the chance that this is right seems low to me. Okay, well, this is the paper that claims this then, basically.
No, I can ask about it.
Oh, the computer program 21 is able to make the given grammar deterministic. For all states x, y, with transitions like this, there must be states the set of normalizing terms is rational. So that's claiming that it's an automaton language. Okay, so let's look at reference 21. Oh, look at this. Let's see if that's still there. Let's see if there's a floating finite automaton on. Oh, great. This doesn't, I have to type this in. Let's see, got Leipzig. .de/tilde whoever that might be, /rx. Not found.
Well, it's 22 years since.
I know, so let's go look in the internet and the Wayback Machine. See whether we can find a lost, see whether Brewster captured. Oh, look at this, look at this, look at this. We might have it. Okay, 2011, it seemed to capture. Well, let's try 2000. Let's just try 2008. 22 years is nothing. I've got code that just runs after 30 years. Written in our language, of course. No other code. Well, let's see. This is the Wayback Machine on the Joe page. So let's take a look in 2005. That's odd, isn't it? Why would the Wayback Machine have captured that page when it was giving a 404?
That's really strange.
That is sort of common, though, on the Wayback Machine.
But why doesn't it reject it when it's a 404?
Some of them are marked with different colors when it's a dead page, but yeah.
Here we go. Okay, written in Haskell.
I wonder how big the program is, whether we could just implement it.
Well, let's just implement it. Yeah, and we could also use the Haskell external evaluator of Haskell, but I don't
just translate it into.
Yeah, well, let's do
language.
But let's see. This is the documentation. As an unsupported format. That's unimpressive. So that's some kind of, okay, hold on. Let me just.
Or DVI.
Yeah, it's a DVI file, right?
Most portable. Well, it's kind of okay. I
mean, it was very portable format in its day.
There was no GitHub at that time, right?
Yeah, well, there's. All the checks below should return the empty set. Somehow I don't think this is going to run if I press submit here. All right, well, that's not a particularly complicated thing. Okay. So this is these are the grammars. Okay, so that's a grammar definition. Well, that's interesting. It's quite a clean piece of code, actually. If that's really it, then we should be able to translate it without any trouble. Let's just see whether that is it. Let's look at the Haskell source code. I guess I look at version 2.1, which is the most modern available.
Oh, it doesn't archive that stuff.
Well, let's see. Maybe it didn't archive a .gz file. Oh, look, there's a PS version of this. Let's look at that. It's a ps.gz. Something's happening. What the heck? What the heck? Why is it an unsupported format?
Do you have a PostScript interpreter? I mean, it's not PDF.
Oh,
it's raw
no, I
PostScript.
think I do. I'm not absolutely certain. I mean, maybe I can. I'm sure Acrobat would do this, right? I have to save this file somehow. Okay, so I go here and I say save link as, and we go somewhere over here and save this. I don't have this. It's not as organized as it should be. Disappointing. Okay, that says it's not recognized there, but what I can do here, what the heck? A .gz file should be, let me just do this. This should work. Hopefully the PostScript will not be splat.
Oh, this doesn't
look
isn't
good.
a GC. This is some.
Yeah, the reason it's failing to open is because that's what's in that file.
Mm-hmm.
What's in that file is about this capture. Okay, fine. So that wasn't captured. Well, it does seem that we've got I mean, I don't really understand these online examples. Check proof of proposition 1. Is that, what language is that in?
Well, that's the RX. That must be RX. So he wrote an interpreter, right, for specifying grammars and then implementing decision procedures about these grammars.
But so the question is, where's the grammar? If this is the grammar, we can make our own decision procedure.
No, well, I mean,
We don't know. We'll find out.
Yeah.
I'll have to find out.
Maybe he's still around somewhere, so I could ask.
Yeah, we can just ask him. We can send a mail. always, that's the easiest thing to do with humans, you know, if they're always a possibility that the human is still around to represent themselves, so to speak. Hold on, let me just pull this back up. Actually, I'm just going to save this S Combinator paper. Oh, actually, wait a minute. He thanks Klopp and Statman, both of whom Matthew Sudzik probably knows these people. We should just ask Matthew. Well, okay. Maybe he still exists. Okay. Well, it's potentially it still exists. Good. Okay. In any case, so he claims this claims a decision procedure for termination.
So what seems to happen that if they grow, they do so in a certain regular way, which you can recognize, and then you know that it will go forever.
Right.
I mean, if you see all these subtrees replicating, then you know that it cannot ever get smaller again.
The question is whether inside that infinite growth, there are all sorts of things that can happen. In other words, deciding that it grows forever is not necessarily, I mean, like you can perfectly well have a cellular automaton that grows forever, but yet its internal structure can do arbitrary computation. See what I'm saying? So it can be just...
So, I mean, can it still exhibit complicated behavior even if it grows regularly? That's
absolutely. Absolutely. You want to see an example? I'll show you an example. Trivial to find an example. Here, I'll show you an example. Just for the hell of it, I'll find you a really lively example. Hold on. Let's see, a good one here. My God. Okay. Let's take an example. Actually, that's irrelevant there. Let me just run this for... Definitely not simple behavior, but yet a very regular outer boundary. You see? So I wouldn't be surprised. I mean, there's nothing to say that the S combinators don't do something as wild as that, even though you can prove that the sort of outer boundary doesn't terminate. If you see what I mean. Roman, are you still there?
Hello, sorry, yes, I pushed the wrong button. So, yes, so for the S terms, that would mean that somewhere inside there could still be a lot of stuff. Or each of these subtrees that goes forever could by itself be somewhat interesting, right?
Right. But so the question is, can we make a visualization of what's happening inside one of these objects?
Or maybe we should go back to identifying common sub-expressions, because that would also certainly make the computation faster, because then you don't have to do the same
we can
thing.
hash them. Right, we just hash them. Okay, so let's do... All right, so what we've concluded with functions with S alone is it's a pretty sparse set of functions. Okay, so let's go... That's not yet a new notebook. Common sub-expressions. Okay, so what we want to say, we want to consider something like one of these ones that grows crazily. Well, let's just take, what do we want to do here? We want to say, here, I've got an idea here. Let's just say nest list slash dot this. Now slash dot will allow multiple instances of, okay, so there's a big, crazy, messy thing, right?
Mm-hmm.
So now the question is, okay, so let's say combinator tree of that, okay? So that we think has some common sub-expressions. Okay, so now the question is how we find those common sub-expressions. So we could use level to go into this expression. Let's call this expert 8. How do we find the common sub-expressions? By the way, given that this is just open bracket, close bracket, can't we make a black and white squares version of this? I think we can. I think we were doing that last time.
Yeah, last time we did that, yes.
I wonder where that is. Well, we can just do it again. 2 squares of x bar. And what we want to do here is 2 string of x bar. And then what we want to say is string replace. I think this is what we did last time, actually. String replace s goes to nothing. Am I right?
You were just concentrating on the brackets, right?
Well, we only need the brackets.
Yes. Mm-hmm.
0, close bracket goes to 1. Then we just say characters of that. And then we just say to expression of that. Okay, so now we say 2 squares of %100. Oh, what did I do wrong?
Oh, there were more than one.
More than one what?
I see commas in there, so there's more than one.
Oh. Oh, that's because it's a nest list. Silly me.
Just nest. Yes.
Okay, so this is showing. So now if I say array plot, I think this is what we did last time. We had a ragged array plot. We can just say array plot of that plus, how do we map this? That slash dot, 0 goes to 0.2, 1 goes to 1, and then we say pad right. Do you think that's the right thing to do?
So probably yes. Let's see. Oh. Okay.
Not highly informative. Maybe we can try, is that our minimal? Let's try our minimal grower. Actually, let's try one that one of the lively ones that eventually dies out. So this one here, for example, just to see what that looks like. Okay, so that's what it does when it blobs around for a while and then it dies out. Right? And so a common subexpression here is a leaf piece, which means something that is a sequence here. So a common subexpression could be seen, we could do it essentially with run length encoding of that bracket sequence or something, maybe, or dictionary encoding of the bracket sequence.
Can't we work on the original?
Yeah, we can, and we should.
Tree? I mean, just take all the subtrees and hash them.
Fine, let's do it. Okay, so let's take this thing, x per 8. This is a terminating case. All right.
Just nest instead of nest list.
Yeah. Okay. Okay, so now what are you proposing to do? You're proposing to look at the subtrees of this guy.
Which would be the sub-expressions of this.
By the way, this isn't right. This should have been combinator trees / at x per 8.
Oh.
Okay. All right, so now let's say here, okay, how do we get the sub-expressions? We can say a certain level number, right? If we say this, if we say level EE8, 5, for example, let's try level 4. That's weird. Level 3. Am I being stupid about this? Is this obvious that this has to be? Do I need to turn this into something which is list pairs?
No,
rather than
you
a
have
head?
a deeply nested expression and you want to find sub-expressions of a certain depth, right? Is that what?
Yeah, that's what I'm, but I think it may not be the right thing because I think, let's see, the expression graph of this just looks like that because it's a heads animal. It's a head-based animal, so to speak.
Okay, I see.
You know what? This is another thing we should do. We should make heads goes to true be an option to expression graph. Let's see. Okay, but we can break out of that nesting by just saying, I think I have a way to do that here. That's quite grotesque, but anyway, okay, let's look at this. This, I think, breaks out. So what I think this does, if I'm not completely confused, is that it does that. Okay. We should have a function repository entry that does this. What should it be called? It should be called function application to list or something. Application to list. No, function to list of expa. Okay.
And the other thing you could do is use the new application operation instead on the right-hand side, instead of f comma x, you say f applied to x.
Where?
Well,
Oh,
if
in
you
this
do a
thing
function
here.
to list, yeah, I mean that's the alternative. I mean, you on the right-hand side, you could use the new.
Okay, so why don't we say function to application?
Yeah, so on the right-hand side, instead of f comma x, you would say f escape ap, or application of f comma f x. Yes.
Let's be modern. That's really nice looking. Okay. So now we can do our level stuff.
3 should now work, right? Yes.
Beautiful. Okay.
But that's essentially what the combinator.
Yeah, I was doing before, but right.
Yes.
But now we can say, now in this form,
figure out the levels. Yes.
okay. You know, I'm not completely sold on this kind of moon operator. Oh, for goodness sake. Okay, sub-expressions now. Okay, so then this is AA8, for example, here. So now we say level AA8, comma 3, for example. This is so hard to understand. This is really hard to understand. Okay, that was level 3. So some of these are isomorphic. No, they're not.
Well, maybe you should work from the bottom up.
Okay, well, hold on. Let's do that. Let's say, so if we say level -1, we should get a bunch of S's. Right. So if we say level -2, oh yes, look at that. If we say level -3, oh yeah, this is going to be cool because then that's going to start differing, right?
Mm-hmm.
Except all of those are identical, I think. Okay, I am officially confused. Okay, so let's go counts onto level -n. What's depth of AA8? 11. You know, the number of depth 11 expressions that I have ever dealt with in my life is very limited. Let's okay, I don't understand this. It's unique at every level. How could this be?
What is going on?
Well, let's keep going all the way up to the top. Well, this says that they're all common subexpressions. This says that the lowest level, that everything is a subexpression, which is kind of probably not surprising from the way it was built.
Mm-hmm. So where does it?
So what's happening here, if we say, here, let's do this. That was very swank what I just did. Right, so that shows that at these successive levels, so that subtree there appears here, and everything contains that subtree. Am I making sense?
Mm-hmm.
So And I wonder if this is a general result, that it always it always contains in the container as the container. Which one was I looking at there? Was I looking at this thing here? Okay, let's just try.
But this was much more complicated, right?
Which one?
The Expo 8, right?
No, Expo 8 is what we're looking at.
Oh.
This is the end result of Expo 8.
Okay.
So if we do the same thing, let's just do this again, just for fun, for Expo 10, but it's going to be the same thing.
So how do I see which levels have more than one?
None of them have. Oh gosh. You know what? This is one of these, the animals are always smarter than you are. That's crazy. Look at this. One of these levels has 3 cases. Look.
Yes.
See, there it is.
Yes. That's what I mean. There, and if you go down, I mean, there's again 3 cases, and so that these are the common the different common sub-expressions, right? But if you go enough down, then there isn't much left to be different, right? I mean,
right. So that's the non-trivial level.
So if you look from the end, then you have 1, and then you have 2. And then you have
no, well, yeah, right. So let's just do, if we just say, oh my gosh, this is so crazy. I mean, these things, there is no theorem that's true, which is why I don't believe that guy managed to get it right.
Well, but I mean, if you look at it, I mean, there are only 2 different sub-expressions.
No, there aren't. There's one with 3.
Yeah, but I mean, yes, but I mean, there were 2, and then one of them branches again, and the other one stays. So there's really not a lot of different stuff going on.
Let's try it one more time. Look at that.
Yeah, so all those dangling branches are all the same, right? I mean,
yes, they are.
So
yes.
So it looks interesting, but I mean, it's kind of a fractal thing, but it doesn't have a lot of different.
I'm telling you, I've hunted these things for so many years. This guy is not as simple as you think. I mean, it has some dressing that looks simple, but it has something going on that isn't quite as simple as you think. I'm pretty sure. Now,
what happens if you add one more S there? So no, I mean the starting expression, right? You're always starting with the same.
Yeah, I know, but if you just randomly add an S, it's going to do all kinds of crazy things.
But you're not.
No, I know. I just want to.
No, the expression you start with is always the same,
right? Right, but I'm saying if you add an S to the expression you start with, I'm saying I don't think that's particularly interesting. Why would that be interesting? I mean, you have to try some other expression. I mean, what I think is interesting.
Okay, I see. You found that one earlier by that as one of those that exploded. Yes. Okay, now. Yes, that
Right,
makes
but
sense.
so what we can go over here is we can look for other ones that explode, right? And we can see whether all the ones that explode have the same properties, right? So here we've got 2 exploding ones, right? So 5, 6, 7. Well, actually, let me just get the 5 and 7 cases here. Okay, neither of those is what we were doing. Okay, so simplest init, simplest expanding cases. Okay, so then here, what we want to do is the analogous thing. Let's just try to put that one first. Okay, so that one has a difference in that case. Okay, so now let's do it for the other one. So that's interesting. That again has a pair there. One's a 2-3 and the other's a 5-3, but they have very much the same structure. Yeah, those have really the same structure. And in fact, look at this. That subtree is the same. So what may be the case is that every exploding S expression has common subtrees. Right, that if you look at the subtrees of anything that will explode.
Yes, so there aren't that many exploding cases, right? It's all basically the same thing.
Yes. But I mean, there may just be one exploding case. Let's find out. Okay, so here we want to know.
Where was that really crazy one?
This one here.
There was one that just was a pop on the screen because it was so huge.
Well, right, we can try some of those, but I mean, I mean, like, okay, so let's. How do we want to figure this out? The exploding cases, we want ones whose vertex out degree, right, doesn't. I mean, one thing we could do is just look at the case where, well, we could just do a fixed point list. Let's see. We want to know whether the thing reaches a fixed point. Yeah, one thing we can do is just do another combinator step and see if it's fixed after some number of steps. But
I mean, just evolve them for a number of steps and see which ones are the largest one afterwards.
Well, yeah, but I mean, so this, for example, here, we can do that. That's line 41.
I mean, here was that really crazy one.
I know. Select from line 41. Those ones were vertex count. Well, actually, let's just do vertex count. Okay. Which ones would you like to pick?
1956.
Well,
3076 is even better.
Yeah, I know, but how
Yeah.
big do you think the cutoff should be? See, I think we need to actually compute something to know whether the thing is going to has reached a fixed point. What would the Ks do if we added them into these? They would do practically nothing. They would just prune these trees down, wouldn't they?
Yes. Now, of course, when you add K, then you get I, and then you will soon stumble on SII, applied to SII, which is one of those non-terminating ones. But well, actually, you have non-terminating ones here as well. So
Yeah, I don't think there's
they would clearly, I mean, S and K together would give you cases where you cannot decide whether it ever holds or not, because you can build a fixed point combinator on other strange animals or birds as they are.
Right. What does the fixed point combinator? So the fixed point combinator takes a combinator and it has a combinator. What does it do? It has a combinator expression which says y of f.
Yes, I mean, the construction is so that fixed point combinator y, I mean, it's not unique. I mean, there are several ones, but y of f can be proved to be equal to f of y of f, or some of those even reduced to f of y of f. So you can use these reduction rules, and after 4 or 5 steps, you get f of y of f, and then after another 4 steps, you get f of y of f. So you build that infinite fixed point. And I mean, the property of combinators is that every combinator has a fixed point. But usually these are non-terminating or infinite expressions, but every combinator has a fixed point. And the consequence of this is that every equation involving combinators has a solution. That's kind of a nice property of these combinators.
Right, although the solution might be infinite.
Yes, I mean, you cannot, I mean, because it's usually in terms of the Y combinator. So, I mean, it's like finding a fixed point. If the argument is numerical, then usually you can find a fixed point in finite terms. But if the argument is symbolic, then the fixed point is f of x applied infinitely often. That's always obviously a fixed point, because infinity plus 1 is equal to infinity. But that's not
Well,
that
but
useful.
if you represent it in terms of transfinite numbers, it may be less trivial, right? Just saying it's an infinite fixed point, you may be able to label those infinite fixed points by transfinite numbers.
We have to be careful about cardinals and ordinals, right? If you go to
I think they're ordinals, right? Because they're ordinals because they are trees. If I'm not mistaken, isn't the Cantor normal form some kind of, you can represent that in terms of trees, as I recall. In other words, given one of these trees, if I elaborate this tree infinitely, the claim would be that I'm going to get something which corresponds to yeah, which let's see. So the thing that we still don't know, and we should probably wrap up soon for today, but let's see. So what we're finding here, so the supposition is maybe all exploding S expressions have the same fuel, so to speak.
Or at least only a very small number of different ways of growing.
Let's determine if that's the case. We should be able to determine if that's the case. So what should happen is, what we should see is that there's a subtree that is the growing subtree. That's the subtree from which all the growth happens. Let's see. So what that is in our multi-way version of the thing, which is over here, let me think here. So what we want to show, we want to find all those S expressions that do not terminate. Richard on our live stream is pointing out that some of these SK combinator is equivalent to the lambda expression that generates hyperoperations. Yes. I mean, we indeed have that, because I know what that is. It's in the NKS book, the one that generates tetration. That is this crazy puppy. This is the combinator. This is the one that is E of X and Y is X of X of Y. By the way, we should be able to represent that as a, let's actually do that. Let me see. I thought I had done this. Wait a minute, second. Okay, so the tetration combinator is E of X and Y goes to, according to NKS, X of X of Y. Okay, so we should be able to get that combinator in terms of S and K, right? So if I say 2 SK combinators of X of Y, comma XY, there I have it. So that object, if I look at that object, well, let's see, that object is being applied to, so what this says is, what do I say here? Conditions. Okay, so this says that's an interesting claim, that this quantity remains fixed through the evolution. Okay, so this thing says E of E of E okay, so Richard is giving us a general hyperoperation. That must be an Ackermann function, basically. Let's take a look here. Okay, lambda. Why is there an R there? What's that doing?
Well, that's the R from the first lambda.
So what is this in?
The first argument. So if you want to see what it is in combinators, you would have to turn this into.
Oh, so if I write it as function of this, function of B, R of function of E, comma, function of X, comma, function of F, comma, E of F. What does the BXF mean? Is that left associative?
E of X, left associative, yes.
Is that right? Applied to function of H, function of E, bug.
I'm on it.
No. It's not your kind of bug.
Almost sounds like an insult.
Yeah.
Oh, yeah, there must be missing close bracket somewhere.
Yes. I don't think this is quite right. Richard, we need a different version of this. This isn't right. But there is clearly a way of representing an Ackermann function, which is basically what we need. Using these combinators.
Yes. Now the problem is with all of these recursive ones, to actually represent it, you have to first formulate the conditional, say if X is 0, then this, else that, and then you have to solve that recursion, and that means applying the fixed point.
Yeah, but look, I have a vastly simpler version of it. I just have this E of X blank Y blank goes to X of X of Y. The rule can only apply to the inner part of an expression. Oh my God. So this is saying that the thing eats away using this function. And it reaches a fixed point when the depth reaches 0. My gosh.
And now here, of course, the question is, if you now express this in terms of S and K, then you probably have to be careful about the evaluation order. Now, if you express it in terms of E alone, then...
No, I agree, but I think what's true is it does terminate. And so the terminating, this result here may depend on the evaluation order, but the fact that the final result is let's see, any expression can be represented. Oh, actually, it's not tetration. It's 2 to the 2 to the m, it says here. Let's see. Oh, no. Always evolves, but for initial conditions, yeah, okay. Of size n, it can take roughly n iterated powers of 2 to do so. This is a nice example, by the way. Oh, somebody has a version of... Okay. This is in terms of lambdas. Yeah, right. Yes, you can do the silver Eratosthenes in terms of lambdas. But now, so could it have been that the S combinator alone has been lurking as a universal system for 100 years, never being noticed? I think it's possible.
By universal, but if it has such a regular growth, then I mean, universal would imply all kinds of...
It implies that that you can encode that it's possible to program it to do anything. And what we're seeing...
But if it's if it's decidable whether it stops or not, then how can that be?
Well, it may be... Let me think about that for a second. See, the real question is, I'm going to be really surprised if this thing, given how complicated it looks here, I'm going to be really, really surprised if it's not universal. But the question is, and let me think about that. Usually, intermediate degrees, for example, are undecidable but not universal. They have undecidable halting problems, but they're not universal. That's the claim. But those things are a fake. Because as soon as you look... Okay, let me think about this for a second. So the claim would be that if there are only a finite number of seeds, yeah, I don't believe it. I don't believe that claim. That because I think it's the same with the Turing machine. A Turing machine, in the end, the whole point is that it could be taken on these explosion seeds, right? Once you hit one of those, yeah, it's just going to loop forever, right?
No, it will not loop. It will grow forever.
It'll grow forever. Great, yes. Fine, whatever. But the point is,
regular way, yes.
Yes, but there's no bound on how long it takes to reach a piece of fuel. So the only way you would get this is if there is a bound on the busy beaver function. That is, if you know it's not going to reach an explosion seed, you can bound the number of steps it takes to reach an explosion seed. Right? The statement that it is decidable... Well, okay, the claim would be...
Yeah, I mean, you see, you can look at it and you can immediately see that it will grow forever or it will die out.
Well, I know. So that's basically the claim that there's a finite procedure for determining whether it will ever reach, assuming there are a finite number of explosion seeds, there's a finite procedure for determining whether it will ever reach one of those. That's the claim. Right, and I do tend to agree that if there is such a finite procedure, then it can't be universal.
Yeah, then it would be interesting to gradually add the other required combinators until we know that there's several sets of 4 combinators that give you the full lambda I calculus, and so you could start out with just 1 or 2 of them and see.
But I mean, look, I think the one thing that is fairly clear is that I think you need at least a combination of at least 3 arguments.
Mm-hmm.
I don't think you can do it with 2 because I looked at all the 2 cases. So then the question is only whether this one, or I mean, honestly, I have to believe if this one doesn't do it, that one of the other ones with 3 will do it. Because this one is, if this one doesn't do it, it's really, really close. Okay.
I mean, that's kind of what we did last time, right? Look at all possible ways of representing 3 different arguments.
By the way, Richard says he's converting it to Curry's BCKW system, but I'm pretty sure that's Schoenfinkel's system. I'm pretty sure that's exactly what Schoenfinkel did. Let me just look it up.
Well, I mean, BC is an alternative to S, right? I mean, so.
Yes, I understand, but I think that's where, as I recall, let me look here. That's the so-called currying operation. By the way, I do need to get copies of those papers of Engel's, like the one about Aristotle. I don't have that yet.
Okay, I can find them.
Yeah, if we have a publication list which has those in it, it would be really super useful. My God, that's the end of the paper. I thought he had this additional combinators. What's the Z combinator?
I mean, S and C, that's S and K, right?
Yep.
And C, no, Z, okay, I. And Z is what we now call B. That's the composition.
Okay.
And T is kind of twisting, changing the order of the arguments. But I think he goes that way. He starts with S and K and then shows that all the other ones can be expressed in terms of them.
Yeah, okay. Particular functions I, C, T, Z, S, and U. For every predicate f, there exists a predicate g such that the propositional function f of x and g of x is not true for any object x. So he's trying to show that you can derive NAND from the combinators.
Oh, there's the fixed point combinator.
Which one?
Well,
U?
These expressions that on the top page, the last one, US, that you, they usually look like this, 2 terms, the same term twice. So that's something. the incompatibility function. That must be either negation or fixed point.
But basically, he's showing that you can compile things down to and this is the stuff written by Bayman that's half wrong.
Mm-hmm.
Yeah, that doesn't seem relevant. A formula can be written without parentheses, a simple sequence of these signs. That's just not true, is it? Maybe with the Z there it is. But I don't think that's true. I think it has to have parentheses. I don't think this is correct.
Yeah, there must be. I mean, if
Well, so what Schoenfinkel appears to be doing here is, I mean, he's showing he's showing that you can reproduce propositional calculus and predicate calculus from these combinators, which I guess is equivalent to showing universality. I mean, here's another question, which is, are these combinators something that we could ever imagine actually finding useful in functional programming? Or are they just too irreducibly obscure? And what people normally find useful is just, saying, pipelining something or something like this, not one of these weird things that distributes arguments in this complicated ways. Well, anyway, all right. Well, this is interesting. I think, yeah. Well, if you can try and find out about the S thing, that would be helpful. And I think, this concept that everything has a fixed point, but it could be infinite. It's sort of interesting. I mean, I don't know whether you'd say the same thing about a Turing machine. Well, I see. A Turing machine, the issue is, in this case, fixed points happen because there just isn't any rule that applies. So the statement, but it could be infinite, it has to be, is it as simple to describe infinity or not? Yeah. Well, I still am concerned about what, the ordinary combinators, we can basically compile any lambda expression to them. So the question is, what other definition of universality can we use if we don't have the K, so we only are living in the lambda I calculus? Well, still, we know that in the lambda I calculus, we have universality. So if we can take any expression, any lambda expression that is in the lambda I case. By the way, do you know, in the theory of when people make models, like I think Dana Scott has spent years making models of lambda calculus and or combinators. Do you know how those work?
Well, I'm only familiar with one model, that's Engel's graph algebras, because that was also the topic of my thesis, but that's the only one.
How does that work?
Well, it's a generalization of function graphs. So, an ordinary function graph can think of it as a collection of arrow terms. A goes to f of a. And this, of course, higher level, so the a itself could be an arrow term. And in the generalization, the graph algebra, the left-hand side of the arrow is not a single element, but a subset, a set of elements. And the application operation is just how would be repeated list, or what's the function that gives all possible right-hand sides for a rule application?
Hold on, tuples maybe. So you're saying that this
replace list, I think.
Replace list.
Yes,
Yeah. Okay.
yes.
Right.
So you have a big collection of arrow terms, and then so f applied to G is you find all the left-hand sides of G terms that are subsets of f, and then you collect all its right-hand sides. So it is this is just this would be a graph of a function, right? The collection of all such things.
Hold on. I don't understand. So a function, so a standard function like I don't know whether we've got our new thingy working yet. No. Does this at least work? Oh, they should at least make this work. Okay, in any case, if I say a function f of a, you're saying that if I map that over like range of 10, I'll get that. Oops, what do I get? I go the wrong precedence here. Okay, so that's an ordinary function. Well, I could write it as.
The way you represent the function by its graph. So you would have a list of arrow terms where the left-hand side and the right-hand side of these arrows are elements of that domain.
Okay, so here, so for example, I could say something like, I don't know, mod a squared comma 11. Okay, is that what you mean by a function? You mean a function represented in something like this?
Yes, as a graph. No.
Okay.
Yeah, graph in terms of functions, not the one you look at, but.
Wait a minute, what are we talking about? We're talking about this kind of graph. A graph that says this element maps
function
to this
graph,
element.
Yes.
Is this what you mean by a function graph?
Yes.
Okay.
And then if you represent the function by its graph, then applying a function to an argument means to take all the matching left-hand sides of the arrow terms and replace them by the right-hand side. And if it's a proper function, there's just one of them, right? Because it's
okay. So if I take this function here, then what I could do is in this graph, I could just say if it's an ordinary function, then 4 maps into 5 here. If it's a deterministic function, then 4 maps to 5.
And so the application operator, so if you have two functions represented by their graphs, and so the operation of application f applied to G would be defined as essentially taking.
Okay, so the function application is just you run one of these graphs. So it's a graph unioning operation of some kind, where you're gluing these graphs together. You say.
No, you have to be. Let's see. No, this picture is misleading because you are assuming that the domain and codomain are the same. You cannot go from one to. You usually cannot go from one to the next. So. But anyway, if you apply f to G, then you search all you apply the rules essentially to the elements of F. Right?
Well, let's just see what happens in this case. So in this case, we've got this, and our graph in this case with vertex labels is that rather trivial graph.
Yes.
Okay, let's just do range of 5 just to be less boring. Okay, great. There we go. Okay, now what? Now you've got another function going to G.
Now, yes, I mean, for example, you could have, so if you call this function G, let's say you have another function F that is a ground that just consists of a set of numbers. So no arrows at all. Then you could apply F to G. No, sorry, G to F. It goes the other way around. But so you literally search for all the left-hand sides of your arrows that appear in the other set and replace them by the right-hand side. So it is just essentially a replace list operation. You find all matching terms.
Okay.
This is
so
just
I mean,
a somewhat weird way of thinking about functions. You just represent them by the graph, and the graph is a list of or a set of arrow terms. Left-hand side goes to right-hand side. And if you represent functions by graphs, then the function application F applied to G becomes replace list operation, but just finding all matching terms.
How similar is this going to be to a multi-way system, I wonder?
Well, yeah, I mean, that's a good question, because I mean, of course, I mean, you can then generalize, say it doesn't have to be a function. So there could be several left-hand sides that are identical that go to the different right-hand sides. So once you generalize, then you can probably get more interesting stuff. But the big step in going to a graph algebra is that the left-hand sides of these arrows are now subsets instead of just singletons.
Well, but that sounds like it's a multi-way system play. So this seems to be...
Well, I mean,
pretty soon we're going to find your thesis here.
Yes. Okay. So you see the K and S and everything. So
existence of non-trivial combinatory.
yes. So these are, I mean, these are the. So you see here some of these arrow terms. So nested arrow terms: sigma, arrow, rho, arrow S. So these are higher. So and sigma and rho are subsets and not singletons.
Okay.
And then the graph algebra of all subsets is a combinatory algebra. So you have to show that these properties hold, which is fairly easy because that's how you constructed them. Then you have to show
what is a combinatory algebra?
That's a structure that satisfies these combinatory laws.
What do you mean a structure which satisfies them? I mean, what do you mean by a combinatory law? I mean, you mean that the axiom...
the K and S axioms, yes.
So I see. So you think of the K and S axiomatic system.
Okay. So in this K would be a set of arrow terms, an infinite set of arrow terms, and S also. And then you have to show that if you use that application operation, then it does exactly what it's supposed to do with K and S. And you also have to show that it's non-trivial, that S and K are actually distinct. So that's not there's no contradiction in the model.
But so basically the point is that you're saying that the axiomatic form of SK, which I think we have some version of those axioms somewhere.
Well, there will soon be in the axiomatic theories.
Yeah, I thought they were going to be.
Yes, I mean it's happening.
Do you know what they are offhand? Do you know what the axioms actually are? I mean,
well, I mean, for now you can just formulate, find equational proof, and just give the S and K. You say for all x and y, K of x and y equals x, and so on.
Okay, so maybe there's an example here.
I'm not sure. I mean, Jose did produce a number of examples recently, so I'm not sure they are already there. No, it doesn't look like.
Yeah, he should put this in here.
Yeah, that will happen, because now we have proper notation for these things.
Right, in terms of the application operator.
Yes, and the combinators and so on with nice print forms and everything.
What are we doing with the combinators? We have an actual what do we have with the combinators?
Well, just the notation. I mean, we'll have symbols, combinator S, combinator K, combinator I, and so on, and they will format nicely, but they will not have any rules attached, because you cannot just simplify them unconditionally, right? Because otherwise you would always run into an infinite reduction. So they are just there, but equational theories can use them, so you can prove theories.
What you mean they have? What is their print form?
Bold uppercase letters.
Okay. And what's their full form name?
Combinator K, combinator S. Try a recent prototype may already be there. No, probably not. I'm not sure. It's in a branch, but so it's probably, I'm not sure whether it's in a combinator prototype or not. I mean, it just happened today.
Oh, I see. It is nice that after 100 years, we're actually going to be able to slightly mainstream these things. No.
Okay.
All right. But basically, what you're saying is that in terms of these, yeah, so I mean, I can perfectly well write, when we've done that, you can perfectly well write combinator of S of X blank. We can write the rules in terms of.
Yes, but I would use the application symbol because the rule, the equational theories and everything will be expressed in terms of the application and not in terms of construct. Right, so you would say combinator S.
Yeah, I understand.
And so on.
Right. I wonder what I'm going to do for the thing I'm writing up.
No, I'm actually assembling a couple of examples that will already work in 12.2, so I can send you those fairly soon.
Okay. Well, one of these days I'm finally going to understand. I could just ask Dana, I suppose, about this, but oh my God, there's like hundreds of hours of Dana talking about models of lambda calculus. Oh no. I don't know that I can well, is this a model of the typed lambda calculus or the untyped lambda calculus?
Untyped.
I need to understand this finally after all these years. I've known Dana for 40 years, and it's like I should finally understand what these models of lambda calculus actually are. Do you think you understand this, or?
Well, I once did, but that's a long time ago, so I would have to familiarize myself with them again.
Let's see. Optimal reduction of lambdas. What is unlambda? It's a programming language based on. Wow. Okay.
Now, in case you're trying to show something, there's nothing on the screen.
No. I'm just
okay.
playing around here. I wonder how this language deals with evaluation. They don't seem to be addressing that here. Yeah. But where is the concept of evaluation and how the evaluation order works? Because that's the I see. Okay. I think I need to finally understand these models of lambda calculus and gosh. Well, anyway, okay. I think this is right. All right. Well, we should probably wrap this up here. Yeah, Bob is saying we should get Dana to join our live stream, and we absolutely should. And I've been in touch with Dana in the last few weeks, so he exists. And yes, maybe I'll ask him. Yeah, okay. Well, we should probably wrap it up here in a moment. Great. All right. Well, thanks for joining us, people on the live stream, and we will see you another time. Sorry, this got into the weeds. What can I say? I don't quite know whether what are these things? They're the who knows? Okay. Well, anyway, see you another time.